Good morning, good afternoon, folks. Hope you're doing well out there and that you're looking after yourselves and your families. Um, Today's lesson is the next lesson on hypothesis testing from the normal distribution. Okay, and it's going to start as ever with a wee starter for you to do. And this starter looks at hypothesis testing using the binomial distribution. So this is looking back at what we did last year, because a lot of the language and the approaches are very similar between the two. So pause the video here and have a go at this question. Okay, so we're told that the probability of a biased dice landing on 6 is 0.4. And we're told that the dice is going to be rolled 20 times. So we've got a discrete random variable x, where x is the number of sixes in our experiment. Okay, and we know that it has a binomial distribution with an n value of 20, so we repeat the experiment 20 times, and the probability of success is 0.4. Okay, if we want to find the probability that the dice will land on 6 exactly 5 times, that means we're going to be working out the probability that x equals 5. Okay, the chances that we will get 5 sixes out of our 20 rolls. And whilst you can work it out by hand, you can also work it out using your calculator. So you're using binomial PD, and you should get that the probability of getting a 6 5 times is 7.5%, 0.046 as our probability. Okay, then the next question says that Polly thinks the probability that the dice will land on 6 is wrong. Write down the hypotheses we should use to test Polly's suspicion. Okay, so this is where we start using language that is also used for hypothesis testing in the normal distribution. So the null hypothesis, H0, this is the status quo option. So it is that the probability of getting a 6 is 0.4. Okay, so that's what we assumed at the start of the question for our binomial distribution. So that's our null hypothesis, that probability of 0.4 is correct. And then Polly, her suspicion is that probability is wrong. She doesn't know whether the probability is smaller than 0.4. She doesn't think necessarily the probability is greater than 0.4. She just thinks that it's incorrect. Okay, so the alternative hypothesis, H1 in this instance, is going to be that the probability is not equal to 0.4. Okay, then the next question says, uses 10% significance level, find the critical region for a two-tailed test to test Polly's suspicion. You should state the probability of rejection in each tail, which should be less than 0.05. Okay, so we've got a binomial distribution, and we're interested in saying, okay, what events are such that if we got those events, we would think it is unlikely that this probability of 0.4 is correct. Okay, so we're interested in events at the bottom tail. So that's events that might make us think that the probability is less than 0.4. We're interested in events at the top of the tail. So that's the kind of events that we might think would make us think that this probability is bigger than 0.4. Okay, to find this critical region, we want to know, okay, well, what event has a less than 5% chance of happening at the bottom end of the tail, and what event, or something more extreme, has a less than 5% chance of happening at the top end of the tail. Okay. To do this, you need to use your calculator, and this time you're using the binomial cumulative distribution, and you're going to use that to give you the probabilities of each of the events 1 to 20 happening. So getting 1 6 all the way up to getting 20 sixes. Okay, and you're going to find the probability of getting less than or equal to that particular event. Alright, what we should find is that the probability of getting x less than or equal to 3, so of getting 3 sixes out of 20, or something less extreme, Well, that has a probability, that's the first event that happens that has a probability less than 5%, and in fact it has a probability of 1.6%. Now if we look at the top end of the tail, at the top end we're interested in the probability of the event happening or something bigger. Okay, so we're going to have to do 1 take away the probability of x less than or equal to our values at the top end of the tail. And what we find is that the first event which has a probability less of happening of less than 5% is getting 12 sixes or something more extreme. Okay, so the probability of getting x bigger than or equal to 12 is the first time that we get something less than 5%, and in fact that is 2.1%. Okay, the next question asks us to find the actual significance level of our test. Okay, so we wanted to split our 10%, 5% at the bottom tail, 5% at the top tail, but actually when you look at it, we didn't capture 5% because the next value up was bigger than 5%, and at the top end of the tail also we didn't capture 5% because the next one down had a bigger than 5% chance of rejection. Okay, so our actual significance level is what you get by adding the two probabilities of the tails, and that gave us 3.7%. And then the last question says, Polly rolls the dice 20 times and the dice lands on 6 11 times. Alright, so the probability of getting a result of 11 is going to be below our critical region. Okay, because the critical region began at 12 at the top end. So if you get the dice landing on a 6 11 times, then that wouldn't be enough evidence at the 10% level to reject the null hypothesis. Okay, so there is not enough evidence at the 10% level to reject the null hypothesis. Alright, so quick recap from last time. Last time out we said that for x, a continuous random variable normally distributed with a mean of mu and a variance of sigma squared, that if we take samples of that population, then the sample means also form a normal distribution. Alright, with a mean also of mu, but a variance equal to sigma squared divided by n. Alright, and what that's really saying is that if we take samples and we find the means of those samples, they are normally distributed about the mean, but the bigger the sample size, the smaller the variance. Okay, so if you maximize the sample size, then almost all of the samples will have a mean of mu. Okay, if you make this n really big, then the majority of your sample means will have a mean of mu. If the sample size is small, then you've got this potential variation in your in the sample means. Okay, so hypothesis testing with a normal distribution, what we're interested in is whether the mean might not be equal to our assumed population mean, or whether the mean of our sample might be bigger than the mean of our population, or whether the mean of our sample might be smaller than the mean of the population. So, for example, we might have a school where we believe the kids in that school have a bigger than average IQ. Alright, so if we know that the mean IQ for the whole country is 100, we believe that this school has an IQ bigger than 100. So we want to assume the null hypothesis that the mean is equal to 100, that the IQ is 100, and then our alternative hypothesis is, well, what's the chance of getting our particular result, our alternative hypothesis is to say that the IQ of this school, so the mean for this school, is actually bigger than 100. Alright, so we're going to want to look at how likely or otherwise a particular event or particular mean is to occur, given our assumption that the population has a mean of mu. Alright, so you're going to have a null hypothesis and an alternative hypothesis, and then crucially you're going to have a sample mean. All right, and we're going to be able to say, well, what's the chances of getting a sample mean of this given the population mean? And we're going to be able to say that if that mean falls within our critical region, then we're going to have evidence to reject the null hypothesis. Okay, and it's just the same, it works in the same way as hypothesis testing we've done before. You're either interested in the top end of the tail, okay, so that's if you believe the mean of our sample is greater than the population mean, or you're interested in the bottom end of the tail, that's if you're interested in whether the mean is smaller than the population mean, or if you just think that your sample doesn't have a mean the same as the population mean, then you're interested in splitting that critical region between the top and bottom end of the tail. Right, I think this is probably better explained by an example. So let's have a look at an example together, and I'll take you through two approaches to how we might solve that example. Okay, so the mass of cakes produced by a bakery is known to be normally distributed with mean 300 grams and standard deviation 40 grams. Alright, so we have, if x is our continuous random variable, we're saying that it has normal distribution with a mean of 300 and a variance of 40 squared. A new baker is employed. State the appropriate null and alternative hypotheses to test if the mean mass of cakes has changed. Alright, well, so what we're interested in first of all is whether the mean remains at 300, so that's going to be our null hypothesis, or whether the mean has changed, so it doesn't saying that it's got smaller or it's got bigger, but just that it's changed. So our two options for our two hypotheses are going to be that either the mean is equal to 300 grams, okay, so that's our status quo option, or the mean is not equal to 300 grams. Yeah. So we're interested in a two-tailed test here, because we're interested in whether the mean is not equal to 300 grams. Alright, so a new baker is employed, and the mean mass of 12 cakes is found to be 292 grams. What is the p-value of these data, and what is the conclusion of the hypothesis test at the 10% significance level? Okay, so what we're basically saying is that we take a sample of 12 cakes after the new baker is employed, and we get a sample mean of 292 grams. And we want to know now whether that provides us with any evidence at the 10% significance level to reject the null hypothesis, i.e., does this give us any evidence that under the new baker the mean is no longer 300 grams? And there are two ways you can do that. So approach one is to look at the critical region for this test. Alright, so we're going to take our sample mean, and we know that it's normally distributed with mean 300 grams, and then the variance of the sample mean, remember, is our variance divided by the sample size. So it's 40 squared divided by 12. So our sample mean is normally distributed with a mean of 300 grams. And what we're interested in is we're interested in this critical region. So we're interested in this region where we can say that, well, if we have a sample mean of A, then that value or anything below it is less than 5% likely to happen. Okay, 5% or less likely to happen. And at the top end of the tail, we're saying, well, if we've got this sample mean of B, so something above 300 grams, then again, if we get that value or something more extreme, then there's a less than 5% chance of that happening under the null hypothesis. Okay, so we want to find these two values when the sample mean is less than A, when that's equal to 0.05, and just from a calculator perspective, alright, but thinking about what we need to put in our calculator on the inverse normal distribution, we want to find the probability that x bar is less than b when that is equal to 0.95. Okay, so that's going to give us this value at the top end of the tail. So what that tells us, if we put that into our calculator using the normal distribution and find the inverse normal, is that the critical region occurs when x bar is either less than 281 grams or x bar is greater than 318 grams. Alright? And we would be able to say at this point, well, as 292 grams does not fall in our critical region, so 292 grams is here, is not in our critical region, then we would be able to say there is no evidence significant at the 10% level to reject the null hypothesis. Alright, so approach 1 would be to find the critical region. So find those values of x bar that would mean we reject the null hypothesis. Approach 2, which is maybe slightly easier, is instead of finding the critical region, we find what we call our p-value. Okay, so it's the same idea. We have x bar normally distributed with mean 300 and variance 40 squared over 12. And we know that in our experiment, we have a sample mean of 292 grams. So what we want to say is, well, what are the chances of getting a sample mean less than or equal to 292 grams within a population that has a mean of 300 grams and this variance? So we know now that we're looking at this part of the tail because we're interested in a value that is below the mean. So we're going to find the probability that x bar is less than 292. And you find on your calculator this is equal to 0.244 to 3 decimal places. So again, we've got the same conclusion arrived at from a different perspective, and we can say that because the probability of x bar is less than 292 is equal to 0.244, and then that's bigger than 0.05, there is no evidence significant at the 10% level to reject the null hypothesis. Okay, so for hypothesis testing on a normal distribution, what we're interested in testing is how likely is it to get a sample mean of a particular value given a particular null hypothesis about the population's mean. Alright? Very similar in your approach in terms of testing the top end or the bottom end of the tail. And I'd like you to go on now and try and complete exercise 18b. Okay, good luck. Stay safe out there. Goodbye.